Thanks for your attendance. I'm happy to present our recent work called Towards Robust Off-Policy Learning for Runtime Uncertainty. You may wonder, what is a runtime uncertainty? That's a new concept we propose and one of the most important contributions of this work. Let me use 3 examples to introduce the runtime uncertainty. First, in the e-com setup, we have a summary recommendation system that gives a personalized recommendation of items to each individual customer. Such a recommendation policy is usually built upon an assumption that the item is always abundant. However, in practice, we can encounter situations where the item runs out of stock, and thus the policy cannot be used. In most times, a new policy will be used to recommend substitute items for the one in short. So you can see the original design policy is replaced by another one when the stock availability is a problem. In a network case, for example, e-commerce, music website, movie website, so to speak, there is also some recommendation system that works well in the usual time. But in some special days, like holidays or some special events occur, there can be a flurry of customers that overwhelm the system. In this case, the personalized recommendation policy will be switched to the default one without personalization to deal with the unexpected huge volume. In the autonomous driving scenario, the self-driving vehicles can confront some bad events that its monitors can hardly observe, like the rear-end collisions, the flying objects, or some harsh weather or intrusion events. In these cases, the design policy will be replaced by an emergency policy. For example, emergency brake. You can see that in all the above 3 examples, the context might not be changed, but the policy is changed because of some unexpected rare events. That's the definition of the runtime uncertainty, which means that the original policy is replaced by some real-time policy due to such uncertainties. Let me use a graph to further illustrate this concept. This is a typical graph notation for Markov decision process. X1, X2, X3 are the states. A1, A2 are the actions. P is the transition mechanism, and pi is the policy. When the runtime uncertainty affects the second stage, the original policy pi will be changed into policy pi tilde. In the following slides, we use pi 0 rather than pi tilde to denote the runtime, real-time policy, which can incorporate historical runtime uncertainties. One crucial property of the runtime uncertainty is that it is unexpected and rare. For example, in this month, we observe some abrupt events, but they never appear again in next month, and some other events occur. So we cannot model the runtime uncertainties by learning the log data. Then how do we handle the annoying runtime uncertainty? We want to bring some robustness to such uncertainties to our method. Our solution is a max-min framework. Suppose we have a value function with respect to the policy pi. We have to design and the policy pi u that generates log data. We specify what kind of value function in a few slides. Then our goal is to search in a set u alpha that concentrates about the logging policy pi 0 for the worst one that brings the biggest adversarial influence on the value function. Alpha here reflects the strength of the runtime uncertainty, which hinges on practitioner's prior knowledge. We choose the L-inflating ball at the set U alpha to allow the point-wise adversariness. Then we pick the policy for future use that does the best under the worst case. Note that our framework is similar to the scientific analysis, which is used to handle the unmeasured confounders in observation studies. They are similar in that both cases consider a L-infinity ball in the minimax optimization. However, they differ in some essential aspects. First, the sensitivity analysis searched for the adversarial direction from 0, while we start from pi 0, which means that robustness is policy specific. Second, the perturbation of confounders is independent of action, while that of the runtime uncertainty depends on the action. Given the max-min framework, there remains two unsolved issues. First, what value function to use? Our solution is an average potential value we will introduce in next slides. Second, how to solve the max-min optimization problem? If we can solve the inner mean problem given each pi, we just need to maximize the solution of the inner problem. In practice, it is often implausible, so we find out a lower bound of the inner minimum problem and then maximize it. Now, let's talk about the first issue, the value function. We first define a concept called potential value. A potential value R of AX is the value that would have been observed if the individual with context X received action A. Here, R of AX can be metric of interest, revenue, the click-through rate, so to speak. Then we can define the average potential value. We take the expectation of the potential value R of AX. Given the context X, we revert to the login policy pi 0, which can be expressed as a weighted sum of the expected potential value given another action A tilde and the context X times the probability pi 0. Let me use an example to illustrate this concept. Suppose an item is tagged with the price A, while the true price just by the market is A tilde. When A tilde is larger than A, expectation of R of AX given A tilde and X reveals how the customer may react to the lowered price. If she thinks the item is in lead, she might feel the lowered price is a good, and thus expectation of R of AX given A tilde little x is large. If she thinks the item is not necessary, then such expectation will not be much different from that when the real price is higher or even lower. In theory, averaging all possible actions A tilde forms a comprehensive and systematic evaluation for any specified action A and the context X. That's why we are interested in this value function. Next, we tackle the second issue of the max-min framework, how to solve the max-min optimization problem. We consider three common estimators, that is, the reward model estimator, the inverse propensity score estimator, and the W robust estimator. The reward model estimator estimates real values in all cases and average them out. We figure out a lower bound of its corresponding value function on the right-hand side. Here we have to skip the derivation due to the time limit. If you are interested, we can talk offline. The inverse propensity score estimator uses the observed value but reweight it using the inverse login policy. On the right-hand side, its lower bound is a solution of an convex problem, so it's easy to solve. Finally, the W robust estimator is simply a combination of the reward model estimator and the inverse propensity score estimator. It is called W robust because it is consistent when either the RM estimator is consistent or the IPS estimator is consistent. Its lower bound is also a combination of lower bounds above. Here we present the exact algorithm to apply the max-min framework to the W robust estimator. It turned out to be an EM algorithm. Each round, we minimize the inner problem and get a worse login policy that accounts for the runtime uncertainties. That is specific to the last round login policy. Then we figure out the policy that works best on such login policy. Finally, we use a real-world experiment to demonstrate the performance of our method. We use an online data from a major e-commerce website in the US. We consider contextual bandit to personalize the daily homepage. We employ A/B testing to compare the runtime robust, doubly robust policy and standard DR policy on 21-day testing period. The evaluation metric is a click-through rate. In this case, possible runtime uncertainties include special offers, stock availability, upselling events, infrastructural malfunction, so to speak. In the bottom table, the orange line is a standard DR policy, and the blue line is a runtime robust DR policy. We can see that the runtime robust method outperforms the standard method in most times. It indicates that by introducing the runtime uncertainty robustness, the online performance can be improved. In addition, we have some simulation results showing that our method is robust to the runtime uncertainties as it is designed. We skip them here due to the time limit. And if you are interested in them, we can talk offline. And thanks. I'm looking forward to any questions and suggestions on this work.